Hello everyone, my name is Carvalho and I will present the paper Cycling Analytics for Urban Environments from Vertical Models to Horizontal Innovation. This work was made by me, Ricardo Pessoa and Professor José in a research partnership between University of Minho and Bosch Multimedia as part of a research project called Easy Ride. In recent years, cycling has been increasingly recognized as a fundamental element for the sustainable mobility policies of the future, and cities are investing heavily in the promotion of cycling programs. This rediscovery of the bicycle happens for three main technology trends. The first is the shared bicycles, helping people ride a bicycle almost everywhere without the burden of having one. The second is electric bicycles, making it easier to travel on steeper roads and over longer distances. And connected bicycles, that are the extension of traditional bicycles, equipped with sensors, processing and communication capabilities. The vision of smart cycling has been emerging as the shared, real-time and collaborative application of data, communication and services to help move people individually and collectively across the urban environment. Recent years has seen considerable interest in the application of mobility models to cycling, or even in the development of new models addressing specific cycling needs. Many mobility models have been proposed to represent particular dimension of the cycling reality of a city or a region. And these mobility models often include compound indexes to assess bikeability or bike friendliness, custom tools to estimate the potential for cycling or the economic value of cycling, and few commercial services based mostly on data from mobile applications. There is also a very broad range of smaller and more focused models, serving specific perspectives of analysis such as hilliness, pollution, route choice, comfort, or accessibility. These models are often published as open source projects, and overall they represent a wide spectrum of analysis of the many dimensions of urban cycling. However, despite of these efforts to develop new solutions and new mobility models for the improvement of cycling, the full potential to be a transformational force for the urban cycling still seems to be unfulfilled. In this work, we hypothesize that the root problem behind this lack of generic models and analytics might be their development paradigm. Despite being a very flexible process, since there is no need to consider generalization, this process leads to monolithic and segregated models. Usually, it involves a deep specialized knowledge where, in the end, only a small community of users with strong technical knowledge on how to prepare, process, and explore this type of data is able to work with them. Also, this paradigm does not support incremental innovation. When someone wants to apply a model, basically they need to start from beginning. And for this, they become hard to apply to different scenarios other than the original one or to different datasets. And this blocks their full potential. And this problem has a huge impact for everyone, municipalities and urban planners, who miss ways of understanding the cycling reality and improve it, and for cyclists who are invisible for urban planners and do not have their needs targeted and solved. So, we established two main objectives. The first one is to validate the prevailing existence of generic functionality across some of these models and characterize the corresponding opportunity for horizontal services that could facilitate their development and convergence. The second is to make an initial analysis of how a digital platform strategy could provide a more promising approach to address the problem and bring many of those models into a common system with added value for different cycling stakeholders. In order to make our initial validation of the overall approach, we started by choosing and analyzing three commonly used cycling mobility models. Then we decomposed those models into atomic and generic operations, and then we analyzed the existence of shared and generic operation across those models. And finally, we combined general principles of digital platforms with the results of our study. This helped us understand how a digital platform strategy could provide a more promising path for addressing this type of problem. The three models chosen that can be representative of models that can be used worldwide were the Illinois model, developed by U-Shift Lab. This model takes a digital elevation model obtained from an open source repository and a set of street map network data. And this model classifies network segments according to the respective cycling effort associated with street slope. The second was the accessibility model developed by David Ball. This model takes an original destination matrix with travel costs and data for opportunities found at each destination and classifies city areas according to their accessibility. Connection costs can be very diverse, for example, travel time, distance, slope, or risk. And the third was road characterization developed by our team. This model takes a set of cycling tracks and OpenStreetMap road network and tries to classify the network segments according to aggregated properties such as average speeds, acceleration markers, stops, turns, and volumes. This map shows the result of applying the Illinois model for the city of Praga. Here you can see the roads in green that are the easier to travel, and in dark red the roads with a very high slope that are almost impossible to travel. And this information is very useful to the cyclists that helps them to choose the best route based on the desired slope or allowing them to set up a maximum limit on their journey to their destination. This diagram shows all the steps that we needed to make in order to reproduce the final map. So we started by obtaining and cleaning the network data, then obtaining the altimetry data and combine it with a road network. Then categorize the road network based on the slope and finally visualize the final result. However, this process is very self-contained and can be seen as a black box. And just like this process, there are plenty of other models that follows the same methodology. However, this model could be separated in multiple different smaller models or components. For example, a model for systematically obtain and clean road network data or reference visualization for this type of data. These smaller and more specific components could then be combined with others developed by other people. For example, one could create a global proceeding for cleaning and correction of road network data, and then the output of this model could be eventually used by another model already done, for example, a slope model. After, one could create a generic tool for visualization of the network data supporting the data obtained from different models, not only the slow but others. And this new methodology could allow people to develop a more specific and efficient solution for a smaller problem without worrying about implementing all the steps for the solution. After analyzing all the three models, you obtained the following list of possible abstractions. Get street network data from OpenStreetMap. This requires domain knowledge about the usage of OSM API, and there is an implicit spatial scope that makes this operation specific to the implementation, and the output data is generic. Get shapefiles from region boundaries. This requires domain knowledge about the availability and integration of region boundaries. Annotate network with slope information. This requires domain knowledge on how to obtain and apply elevation data for a concrete region, and output data is also generic. Classify a route network according to a cycling effort model, and this requires knowledge about classification models for cycling effort. Estimate accessibility from OD matrix and opportunities, and this requires domain knowledge on classification models for accessibility. Map matching route points to OSM points. This requires domain knowledge on map matching methods. Compute average speed for road network segments, where code can be reused with any compatible route data format, but ability to aggregate multiple routes is essential to this process. After identifying these abstractions, we combined the properties of a digital innovation of digital platforms on the cycling analytics problem, and we obtained the following set of key properties. First, the platform should be specific for cycling and be focused specifically on the needs of micromobility. While sharing many principles with more mature forms of mobility analysis, cycling is nevertheless different in regard to the nature of data sources, route classifications, key performance indicators, or the role of real-time data. Second, a basic premise for any digital platform is the ability to congregate many users and very different types of stakeholders. This convergence should bring together many cycling stakeholders, such as bike sharing operations, bike shops, city and mobility authorities, business, citizens in general, among others. Third, the need for cycling services is a global need. Therefore, the proposed platform should offer a broad set of tools, services, data and algorithms to address the cycling challenges of any city in the world, regardless of its characteristics or its level of cycling readiness. The scale associated with the global services is essential for reaching the critical mass that is needed for the platform to be perceived by others as a catalyst for convergence. But this platform should also connect to local cycling ecosystems by promoting local cycling groups or to allow access to detailed information about the local infrastructures and regulations. Collective intelligence. This platform should have the capability to observe and learn about cycling mobility in a way that supports optimization and informed decision-making at multiple levels of the system. Under a smart cycling paradigm, the bike should no longer be a single isolated entity. Instead, it should become a vehicle that can sense and share data, that can interact with other vehicles on the road, that can learn from its environment and learn by the way it is used. Horizontal innovation. A platform should provide a horizontal technical foundation upon which many complementary products and services can easily be combined, each offering its set of knowledge-intensive features. This should lower the barrier for new innovations, as they can more easily emerge from simpler new models or from the multiple combination possibilities that can emerge from repurposing existing models across many users' contexts. This would mean that many more and more advanced models could quickly emerge, and progressive decomposition and convergence. From the results of this study with mobility models, we can identify the need to promote convergence between many independently developed analytics models. The platform may promote some convergence by facilitating the use of canonical data formats for representing the most common types of data, while totally optional, a few well-known data formats for common data types promoted by an extensive collection of conversion and aggregation functions may offer a shared resource that make data convergence simpler whenever suitable. Regarding the algorithm of those models, the convergence process should promote their decomposition into basic steps. Each model needs to be described in a way that formally defines the model generation process as data flows, with specific data sources, transformations, concrete parameterization of the algorithms, and concrete and published outputs. This should have a major impact in the development of new cycling mobility models, reducing the development effort and potentially improving their overall quality. Despite of only analyzing 3 models, in this work we have shown that commonly used cycling models are composed of basic processes that have a high potential to be used as horizontal features in the context of a digital platform approach. This represents an initial validation of the problem and highlights an opportunity for a new type of solution based on a platform strategy. We also identify some of the dependencies that are often embedded in the implementation of those models and prevent them from being widely repurposed by people outside their initial development context. These are fundamental hints for understanding how they can be redesigned around horizontal features shared among multiple model implementations. Building on those results and on the general principles of a digital innovation associated with digital platforms, we outlined a set of key design principles for the development of a digital platform strategy for cycling analytics. As future work, the main research line is to develop a technological platform that implements these key properties identified earlier. This platform main capability should be to process data and generate new knowledge about the cycling ecosystem, and the capability for aggregate data from different and heterogeneous data sources without many restrictions for the developers. One can use the data format that best suits him and promote convergence. And this platform should also support an API for the creation of public services and deliver this new information generated. And a portal with ready-to-consume data and services to help people have new insights of their city without the need for having specific knowledge on data processing and deep understanding of the mobility models used. Thank you all for your attention. I hope you like this presentation. I'm open for answering any question. Thank you.